Okay. Um, Lakehouse Migration Advice. Our speaker today is Levani, and the floor is yours. Go ahead.
Hello, everyone. Yeah, today I'm gonna be speaking about how we use Apache Iceberg at Wise to power our data lake. So briefly about me, I've been working at Wise for almost 8 years now, and I'm mostly focusing on the stream processing related technologies, especially with Kafka and Flink. And my experience with Iceberg will be from that angle, how it integrates with streaming platforms, especially with Flink and Kafka. So a bit about Wise. So we are a global fintech company. We operate across the world, and we try to build the best way people can hold money as well as transfer and spend money in various different currencies across the world. So as of fiscal year 24, we had close to 13 million active users, moving around 118 billion cross-border volume yearly, and money that is held at Wise by the customers is also increasing year on year. So in terms of engineering and analytics, we are more than 1,000 engineers, analysts, and data scientists, more than 100 teams across 6 cities and 3 continents. So we are not a huge engineering organization, but we are not like small either. So today I'll be mostly, I will have like 3 main topics to discuss. First one will be the ingestion layer, then talking about table maintenance, and like some brief summary at the end. And if my timing is right, I think we should have some time for the questions. But I'll spend most of the time into first 2 topics, which will be ingestion and table maintenance. So let's start with ingestion layer. So at Wise, we mostly operate with GitOps model. So we have internal system where users can submit their intent of like what they want to do in terms of replication. Like they can specify this in some sort of config that is then submitted through a PR and then picked up by our CI/CD workflows. So for example, they can specify that they want to replicate this given Kafka topic, like connect to this Kafka topic, specify some transformations, like how this topic events map to the columns, what are the types, etc., and specify the target, like in which target they want to replicate this data to. In this case, the target is one of the Iceberg tables, and they can specify the partitioning spec and things like that. One interesting aspect about our replication system is that we have this notion of an entity, and this entity essentially references some global configuration that is automatically inherited to all the replication flows that are writing to the target. So, for example, in this case, if somebody is creating replication to the Iceberg table, they will by default get the maintenance configurations, like tasks that they have to run in order for the maintenance and things like that. But I will cover more in details how this maintenance is configured later. Then this configuration is packaged and submitted through the CD workflow. Once it's merged, after validation and things like that are passed on the PR, they submit it to our API. You can think about it as a planner that then decides in which like a replication cluster it should be provisioned. So if there is no cluster available, it might create a new one. YAML is just an example. In this case, it's a generic API, so it can be used by any of the it can be used through the UI, for example, to integrate with the system and so on. In replication system itself is based on Flink, and it runs on top of Kubernetes. So we have various sources that we connect to, like in this case, and we try to limit the amount of sources we connect. So for now we only have support. We support only various CDC sources from various relational databases, Kafka, and file source like based on Parquet, for example. And sorry about that. So then then we can replicate those sources into various destinations like Iceberg tables, Snowflake using Snowpipe ingestion, another Parquet target or Kafka target. And we keep the sources where we replicate data from like limited, and I will cover more in details why we do that. So in specifics about the Iceberg replication, so it's built on top of Flink Data Stream API. By default, all the Iceberg tables support upserts, so upserts are enabled by default, and we have frequent checkpointing, which is like 5 minutes or less. So we update Iceberg tables quite frequently. So let me give a bit of overview of the challenges with this setup and how the Iceberg stream integration works. First one, I guess like not many people here, but quick show of hands, how many use Flink? Okay, quite a few. First problem that we faced is the Flink job, like recovery of the Flink application from the older save point when it writes to the Iceberg table. So to give an overview about how the Flink checkpointing usually works is that you have some timeline like where Flink checkpointing progresses. So for example, if you have interval of 5 minutes, then every 5 minutes you have a new checkpoint, which is auto-incremental. From it starts, let's say, from 1 and up until 11, you have a like checkpointing, kind of continuous checkpointing of your Flink application. And the checkpointing is useful because when something happens, Flink recovers from that checkpoint if you scale up your job or if you scale it down, things like that. The way we do the releases of the Flink application is that when we start the deploy of a new version, we perform this operation, which is like stop with a save point, which clears the Flink state. First takes the save point, clears the Flink state, basically then we have a like save point available for recovery. Save point is essentially same as a checkpoint, just with the extra metadata, and that is stored more separately from the general Flink metadata layer. So once we have taken the save point, then we when the new version of the Flink application then has a kind of a special logic inside of it that recovers if it's an empty state of the Flink application, it tries to check if there is any available save point for that Flink application, and then it recovers from the save point in case of the empty state. And once the recovery happens successfully, then it resumes the checkpointing as usual, so continues to 13 and so forth. The problem with this approach, problem that we faced was that the Flink, we use adaptive scheduler for Flink, and there was a bug, quite recent versions, that if you would restart under certain conditions, Flink might restart the job manager with an empty state. So it would think that nothing is there for the Flink application. So how it materializes in our case is that let's say we took the save point at when it was with ID 12, then we progressed through checkpoints as usual. Then let's say the bug that I mentioned before happens sometime here, then we would our code would recover from the latest successful save point because there would be no state available in a job manager. And we would essentially roll back the Flink state to the version and to the state that it was when it was a checkpoint with ID 12. And we would lose all the checkpointing that happened afterwards, and we would have to go through those checkpoints again once we have recovered from the checkpoint ID 12. So you might be thinking now, why am I talking about this, and what does it have to do with Iceberg? But I promise there is some logic to this. The thing is, when you work with Iceberg, with Flink, at least and I guess with other engines as well, checkpointing is stored as part of the table metadata. So you have the list of checkpoints that are stored within the Iceberg table metadata. So this is the Trino query that queries the snapshots table for the Iceberg table, and you can see that there is a Flink max committed checkpoint ID stored as part of the table metadata. In the Iceberg files committer, then there is this. It is used by, with the following logic, that whenever Iceberg tries to commit new pending data files into the whenever checkpoint happens, there is this check that verifies that incoming checkpoint ID from Flink, if it's more than max committed checkpoint ID that Iceberg has in its metadata, then pending data files are committed. If not, then it is skipped. So it assumes that this checkpoint was already committed, so it essentially skips those data files from committing. This leads to this issue that can lead actually to a potential data loss scenario. So since you could recover your whenever there can be various reasons why you would want to recover your Flink application from an older save point. And in these cases, let's say when you recover from older save point, you might change your job parallelism, you might give it more resources, etc., which might lead consuming more data than it had before. So the lag, for example, that you had on Kafka topic might be consumed in just few checkpoints, while Iceberg would still think that the data is already committed. So it would skip essentially writing any new data files. So it's kind of creates this kind of silent data loss scenario that we have encountered, which wasn't very pleasant. So how we mitigate this issue is we extended Iceberg files committer, which has this now special logic where it checks if the state of the Flink application is restored, so Flink state is restored, then it tries to roll back Iceberg table to the same version of a snapshot that matches the incoming checkpoint ID. So how it works whenever this rollback is triggered is that it gets the first restored checkpoint ID, so the checkpoint that Flink application is recovering from. Then it gets the max committed checkpoint ID from the table. If restore checkpoint ID and the max commit checkpoint ID, if restore checkpoint ID is more than or equal to max checkpoint ID that we see in the Iceberg table, then all is fine. We don't have to do anything about it. But in other case, we try to find matching snapshot for that restore checkpoint ID. And once we find this snapshot that matches that checkpoint ID, then we automatically roll back our Iceberg table to that snapshot, to the snapshot ID that matches the recovered checkpoint. This find snapshot ID is essentially what it does is it traverses back from the latest from the latest snapshot to back it gets the latest snapshot that goes to the parent and sees if the this field in the metadata which corresponds to the max committed checkpoint ID and if this max metadata that is checkpoint ID that is in the metadata, if it's less or equal to whatever we restored for Flink, then this is the snapshot we can safely roll back to. This wasn't actually enough to mitigate this problem. We have also enabled what is called periodic save point, and this is before we were taking save points of our Flink application only whenever we would release the new version. We do a lot of releases of our Flink up in general at Wise, but sometimes it might be, let's say, a day or two we don't release anything. That might lead to save points that are quite old, and which isn't great because it doesn't play well with if you want to also expire your snapshots. One thing to consider is that the save point interval should be more frequent than your whatever your max snapshot age is, so that you don't end up in a situation where you cannot find any snapshot that you can roll back to. Another interesting aspect that we had enabled before is in Iceberg you can specify that delete after commit enabled flag, which essentially deletes the metadata files that are tracked by the Iceberg table to optimize not to store that many metadata files, especially if you do frequent checkpointing. But this doesn't play well with this approach, because in any time, for whatever reason, based on this code, you might have to automatically roll back your Iceberg table to the previous, some older snapshot ID, and those metadata that is for that snapshot has to be there. So we have disabled this flag, and either way we offloaded this kind of expiry and deletion of the metadata files to the maintenance tasks. Second problem, it was already mentioned a few times, I think, the delete files. And delete files when you do the stream ingestion is especially painful. So first part, upper graph essentially shows the metric that is for the committed data files records count, and the graph below is the graph that shows committed data files, delete files records count. Can you spot the difference? Yeah, it's the same picture. So if you can't spot difference, that's okay, because they are essentially the same. And this is done well, because whenever you insert or do the update after and you have upsert enabled, Flink Iceberg with Flink essentially creates the equality deletes for any write, just because. Kind of logical as well, because when you do, like, if you want to do the fast ingestion, you cannot possibly scan the table to see if you have that key already written, right? Otherwise, writes will be really slow. So it creates this delete equality deletes just in case, and offloads this work on to the query engines later on to apply those delete files. So first, if upsert is enabled, we first delete this key for this given row, and only after that we insert the row. So whenever then on the query engine side, is with merge and read configurations, usually whenever you have this Iceberg query, it would get all the delete files for this given query, all the data files, and then apply them during the runtime. So we didn't, like, when we started our Iceberg journey, we didn't have any good maintenance approach, which if we had like very frequent ingestion, it resulted in Trino. This is the heap dump of the Trino, which was spending most of its time actually going through equality deletes rather than actually serving any query. So it was very expensive to do this kind of frequent writes. So basically, when doing the stream ingestion to icebergs and you have upserts enabled, maintenance is not the option at all. Like you have to do it, otherwise query performance will not be acceptable in any way. So this brings us to the next topic, which is like the maintenance of the tables and how we approach it. So our first approach maintenances were like scheduled or asynchronous based maintenances. So approach is rather simple. So you have some source, for example, Kafka topic that consumed by a Flink application in our case, and then writes to the Iceberg table. Then we had periodic maintenance that is run on Spark. That periodically runs those maintenance tasks like rewrite data files, expire snapshots, things like that. So this was our first approach, but it didn't really work very well for us, because when we do this kind of a frequent ingestions, those scheduled maintenance tasks were often lagging behind. So you do like a lot of writes, but the maintenances may take longer. And over time, it was getting to the point where queries were still very, very slow. And in general, like no matter how fast you write, if nobody can read, I guess there is not really a point to write really fast. So this kind of gave us an idea to is should we change the strategy, and with that we came up with this approach, what we call coordinated maintenance. So usually when you work with Iceberg and you look at the Flink topology, you have stream source, like all or any source, Flink source essentially. Then you have Iceberg stream writer, which corresponds to some like parallelism with of your Flink job. And then you have Iceberg files committer, which has max parallelism of 1. So this is your classical topology of your Flink application. So what we added is that we added another subtopology to this, what is called now table maintenance. And this essentially now orchestrates the maintenance of the table as part of the Flink Flink application itself. So as mentioned before, we have this all the maintenance tasks that we have to run on the Iceberg tables are are automatically inherited by the older applications that write into the Iceberg. So here we have the configuration where we say that the maintenance on snapshot change equals 5, meaning that if we see 5 changes in a table, so 5 new snapshots were added, we want to run the following maintenance tasks. So the algorithm, the way it works, is like it is described in this chart. So, but I will try to go over it like bit by bit. So what we do is that this table maintenance essentially doesn't read any data; it just listens to the checkpoint events. So whenever checkpoint happens, first thing it does is checks has this table changed, and it checks this by first getting all the snapshot, maintaining this seen snapshots state. So all the snapshot it has seen so far before the previous run, from the previous run for this table, and it gets the latest snapshot. So if this is a new snapshot ID, then it moves to the next step and it verifies if it's an empty snapshot or not. The thing is with Flink, if you have no data to be written to the Iceberg, it generates an empty snapshot from time to time. So we verify that the snapshot, if it's a new snapshot, does it actually have any data files associated with it? And if it has some data files associated with it, we store it to this seen snapshot state. And after that, we get the seen snapshot state size, so how many snapshots we have seen so far. And if this size is more than what we configured or equal to what we configured, in our case 5, we try to start the maintenance process. We don't start it if the maintenance is already in progress, but if maintenance is not already in progress, then we we do this, we send pause events to the source and we trigger the maintenance tasks. And I will describe what these things do just about now. So on trigger the maintenance event, it essentially starts the maintenance, like Spark maintenance task asynchronously and immediately exits. This is done because maintenances can take a while, so we don't want to hold the checkpointing time for that long. Otherwise, we will have we will hit some checkpoint timeouts as well on Flink side. So maintenances are start asynchronously, and whenever they complete, if the maintenance is successful, we send the resume source event and we clear this scene snapshot state, so we can do this process again for the later runs. So in terms of like source events, I mentioned this many times. Basically, this is like coordination on top of that is custom built by our replication system on top of Zookeeper. Basically, this means sending source event means writing some state in a specific node in a Zookeeper, and there are listeners for each of the sources we maintain. So that's why we are kind of selective of the sources that we want to onboard, because it has to be compatible with this like pausing and resuming mechanism. So in case of Kafka, whenever there is a pause, that means that we pause the partitions. So polling continues, but we pause the partitions, meaning poll just gives us empty consumer records, so there is no rebalancing impact or anything like that. It feels like there is just no data in the topic. And in case of the file sources, we have a custom file assigner that essentially, whenever it says that it has a state of paused, it doesn't give any files to the split readers, which is like Flink's terminology, basically. So again, for Flink's perspective, it just looks like the data is not there in the source, so there is no need for maintaining buffer states in Flink or like stopping the sources or things like that. It just looks like there is just no data temporarily. So whenever if it's a pause event, we do the pause, and whenever there is a resume event, we resume the source. So we don't have anything special for the rewriting of the data files themselves. Or maintenance tasks, we don't have anything like magical for those, but for rewrite data files, we do have one important configuration, which is delete file threshold set to 1. The reason is that when you rewrite the data files, by default, it will be based on the file sizes. So if you have file size that is already quite, let's say, close to 512 megabytes by default, those files won't be considered for rewriting. But if you set delete file threshold as 1, that means that if there is even small files that have at least one delete file associated with it, it will be still rewritten, and those delete files will be applied to the data files. This is very, very important when you do this stream ingestion and you have equality deletes, because this essentially shifts the computation from query engine side to the optimization phase. Another important point when doing the optimization is actually partitioning. Having large partitions or very active partitions doesn't really work very well with optimization. So for example, if you just have timestamp like base partitioning that based on the day, depending on the volume in a single day, you might be writing so much that the optimization phase will still be taking long time. So what we do is that you can also add some next level partitioning, which in our case will be like, let's say, bucketing based on the ID, which takes the hash value of the incoming ID and distributes across, in this case, 10 buckets. That means even in a single day, there will be a parallelization of work when doing the optimization, even though this given day is very active at this point in time. So showing now some results of this coordinated maintenance. Basically, this is one of the use cases like replication flows that we have, which has millions of records written per minute, and it has quite frequent checkpointing. So with this coordinated maintenance, we see that most of the time we are well below under 8 minutes, how long it takes for the optimizations to run or maintenances to run. So we kind of sacrifice this data freshness in order to have well optimized tables. So in practice here, this means that every 15 minutes we have close to 10 minutes delay in terms of like data writes, but that's totally okay, and we can still achieve near real-time freshness. Another use case, same graph, but with a bit different use case, which has more of a bursty kind of output, which writes like tens of millions of records in one go. Even for those use cases, optimization usually runs well under 10 minutes. In this case, first one was 13 minutes, but let's ignore that. But usually it's quite fast. So it doesn't matter. It's like mostly it doesn't matter like how much. If you keep these aggressive optimizations, you still have more or less constant time of how long it takes for table to be optimized. depends on the data distribution, things like that. If you don't have like good partitioning strategy and things like that, then it will be a problem. But if you have good partitioning strategy and aggressive maintenance, then maintenance operations mostly take like predictable amount of time. So like what we spent a lot of engineering hours to actually build this, but it has actually it had a great benefits for our query times. So overall, we have achieved what we think makes sense. It might not be ideal for all the use cases, but for us, I think it's treating ingestion and maintenance as a single unit. I think for our case was very beneficial, because otherwise we might be writing so much that the maintenance cannot keep up, which is not really helpful. And we also noticed that when this source pausing and maintenance run are coordinated, actually the maintenance tasks are actually finishing faster. So especially the rewrite data files action is completing much faster, because it doesn't have any conflicting writes because the source are paused when the maintenances are run. We can achieve like close to under 10-second query performances, even very large tables, more than 80 billion, close to 100 billion of records, and aggregate queries are even faster. And this just to show as well that after this change, our Trino cluster, which is like relatively small, only like 60 pods, is happily doing close to 1.40 billion rows processing per second, and this was not close to this number before these coordinated maintenances were implemented. Just to again show more data about this coordinated maintenance. So we track the on Trino side, we track all the queries that are executed on our Trino cluster, and this is for one specific use case. We have the data from January this year up until April, which is ongoing, and we see that we have implemented the coordinated maintenance with all the fixes, etc. In March, and we see average execution time have drastically improved compared to the February and January. So we are now in average around 13 seconds of the average query execution time, and 6.5 seconds now in April, but we'll see what happens. But yeah, overall it yielded very good results, and yeah, it's visible with comparing with the older stats that we have. Okay, so summary and the future. We love Iceberg. I guess that's the summary. We have moved. We are like transitioning phase now. We have already moved quite important use cases, like what we do with Iceberg is not actual traditional analytics as well. For example, we archive our relational databases into the Iceberg tables, and then clients query all their data from Iceberg, and they keep their relational databases smaller. So this is first use cases that we have onboarded to Iceberg, and we are in the process of migrating even more use cases from Snowflake to Iceberg tables that can be again queried by Snowflake, by Trino, by other engines. So having a storage layer on top of the Iceberg. Some of the future improvements that we would like to see in general in Iceberg, and what we are looking forward to is first one, since we are very much like from streaming perspective, we are very much invested into Flink. So right now Iceberg writer of Flink is based on the Sync v1 API of Flink, and migration to Sync v2 API is in progress. Once that happens, we can even do cooler features like overriding post-commit and pre-commit topologies to add even more customization to how the Iceberg writing happens in Flink. Future of equality deletes. This is very interesting. This is there is a a mailing list thread about this feature, like possible deprecation of equality deletes. But we'll see how it goes. Obviously, all the stream writers are using equality deletes, including if you have Kafka connector, it's based on the same approach. So I guess there cannot be just deprecation. There will be some alternative, and I'm sure the alternative will be even better. But we'll see where it takes us. Right now, equality deletes are useful, but they are very expensive as well. But they do the job that it cannot do in any other way yet for now. Variant column support have been mentioned many times already. It will be really important for us as well, because we have a lot of stream sources from Kafka, from other places which have semi-structured data. Right now we force users to essentially do the fields to column, like extraction of the fields into the dedicated columns, but with this we might improve the user experience, but I guess some level of flattening will be still needed. One interesting thing is there is ongoing work about moving maintenance, like implementing maintenance tasks within the Flink itself. So it would be interesting to test how the Flink maintenance tasks actually work. Will it be faster than doing it via Spark, for example? This is something we are looking into as well. Another big thing will be the RBAC catalog. There have been some talks around this to standardize the role-based access on the catalog level, and it being part of the catalog, which will be extremely useful and important for us as well. And I guess all the other vendors will be just implementing those specs, and this I think will be a really big game changer for us too, in terms of like access control. Just more like a wishful thinking. Right now, the support for the like what type of merge you can do when you write to Iceberg is pretty limited. You can do only upsert. In other open source project like Flink's Apache Pymon, you can do more granular merge operations. Like you can do selectively, you can select which columns you want to update if there is a write on the same key, or you can do like things like first row. So if you have given key already written to the Iceberg, you don't write anything else. You just keep the whatever first was written. This can be really useful for streaming workloads, because often they have this kind of offsets that then later used for the incremental processing. So if the offsets change, then incremental process will think that there is new data written, but actually it was a duplicate or something like that. Right now we run all the maintenance tasks within this coordinated workflow, but there is actually no need to run some of them, like remove orphan files doesn't have to be part of this coordinated workflow. They can be run asynchronously, and they also get like runtime of it can be quite expensive as well, depending how many files you have. So moving this to be asynchronous, I think, will improve our overall maintenance duration as well. I think this is it, all I have. Thank you.
We do have 5 minutes for questions.
I think you mentioned you're using Snowflake as well here, and you're a heavy user of delete files, so I'm wondering if you've had any compatibility issues there.
Yeah, it doesn't work. But we have other special writer for this, which essentially doesn't write equality deletes, but only positional deletes. So we offload the merge operation to Spark, and we write temporary Iceberg tables with equality deletes, run merge operation then on Spark that creates the just ordinary positional deletes. It's much slower, more expensive, but that's an option for use cases which have to have compatibility with Snowflake.
Last time we looked at actually Flink connector for Iceberg, it was able one connector serve only one table. is that still the case? And if it is, so can you serve with one connector, one sink, multiple tables or databases even?
Yeah, that's what we do. You can, we create different subtopologies within each Flink pipeline. So you have one Flink application, but let's say, for example, you get a list of databases, and for each of them you create different stream topology, and they run as a single Flink application. You can also split the stream into multiple outputs, and then independently they can also write into different Iceberg tables.
Okay. And another question is, so we mentioned where you basically stop your sources, let's strictly speak. So did you have to customize Flink sources to do that?
Yeah.
Okay.
Yes, it's mostly it's based on most of the Flink sources have a public API for this kind of customizations. Like for file source, you can give your own file split assigner that essentially assigns files to splits. So we have given this custom implementation for it. And for Kafka, there is also you can override Kafka source where you can say which partitions need to be paused or resumed. So they are somewhat overridden. So it's not hacked into, but it's based on the public API, just more customization.
Okay, thank you.
Hey, thanks for the talk. You have a very kind of nuanced architecture with a lot of moving pieces, and I'm kind of curious sort of what the evolution of that looked like. Were you guys early adopters of Iceberg? Can you talk about the path, maybe about how you ended up with, this architecture?
I think the value proposition of Iceberg, so in our case, users want more real-time data, more fresh data than we had with Snowflake. Snowflake, we had non-real-time use cases. With Iceberg, I think one of the reasons the way we try to push is that we can support more real-time use cases as well. And for that, we start from the point we started working on Iceberg. This was our primary requirement to be able to serve, to have more fresh data compared to what we had before. We were not early adopters of Iceberg. We started the journey around 2 years ago. I guess that doesn't make us early adopters, but we just, from the beginning, our use case was around real-timeness, and we just discovered all the challenges associated with it as we moved forward.
Thank you.
The final use cases can you talk about a little bit the actual final use cases towards the user?
Mm-hmm.
What are you serving here?
For example, there can be analytical reports that have to be refreshed more frequently, not just daily, maybe on hourly level, maybe even more frequently. There are use cases the way we organize tickets for our customer supports that have to be more real time and things like that. So it's mostly analytical use cases that also is part of the operations of Wise.
Okay, so there's not a lot of machine learning for use cases like fraud detections or
That
things
too.
like that.
That too, but
okay.
that's mostly is built on the just stream processing itself. At this point, Iceberg
I
doesn't play part in that.
So you do have a separation then between the analytical and the machine
Yeah.
learning use case. Okay, thank you. Sorry, anybody else? All good then? Oh yes, then.
I'll try to keep it short.
Yeah, it's okay.
So earlier in the talk, you talked about the submission process for users, creating a PR, configuring a YAML. What do they think about this? Do they like it? Do they appreciate this process? Was it easy to introduce?
They love it because they don't have to.
Who are these users? Are they data scientists, data
Yeah.
engineers?
It's mostly data scientists and analysts. They are, but to be fair, we had similar process for years already. Maybe the people are just used to it. So we had similar process for Snowflake replications where they configure those flows using YAML. But we acknowledge that these YAML-based configurations might get a bit weird but we try to keep them as simple as possible and infer a lot of configurations automatically on the backend side.
And on this note, this section is officially over. There's not going to be like another talk in here, but there are other talks in other sessions in 15 minutes. So grab a coffee, and I'll see you there.